In this video, we're looking at a two-part kinematics problem. So we're given a car of unknown mass. It's just called m. It accelerates from rest for a given distance of 100 meters at a given rate of acceleration, 5.50 meters per second squared. Then suddenly at the 100 meter mark, the driver slams on the brakes and just slides the car to a stop, and our kinetic friction coefficient is given as 1.0. That's an approximate value for rubber on concrete, so this is somewhat realistic. And in part A, we want to get the speed before the braking occurs. So it's the speed right at the 100 meter mark. And then in part B, we get the minimum stopping distance. In other words, how far does the car slide before it comes to rest? So for part A, during the acceleration process, we have a known value of the acceleration. That's 5.50 meters per second squared. And we know the displacement. We can assume the initial position is 0 and then say the final position is 100 meters. And we're interested in the speed of the car at the end of this process. Well, there's a time-independent kinematics equation that makes this as simple as possible. And that's v squared equals v naught squared plus 2a times the quantity x minus x naught. That thing in parentheses, x minus x naught, is just the displacement of the car, which we know is 100. So our initial speed, v naught, was 0. The final is what we're interested in, and that's conveniently already isolated on the left-hand side of this equation. So we'll go ahead and take the square root to solve for that. And I plug in twice the acceleration, which was 5.5, and multiplied by the displacement, which was 100. Into 3 significant digits, I get a final speed of 33.2 meters per second. Now, part B is a little more difficult. It's not just a pure kinematics problem. We have to figure out first how big the acceleration is caused by a kinetic friction. And once we have that acceleration, then we plug into a kinematics problem. So we need a simple force analysis on this car at the moment it begins braking. So there's the weight of the car pointing down. That's the force of gravity. And then I have the normal force pushing up. There's nothing tampering with this system in the vertical direction. So that normal force has to be exactly balancing the force of gravity. And we'll go ahead and write that force of gravity as mg. We don't know the mass of the car, so it's just mg. The normal force must be equal to that same magnitude of mg. Then we know the kinetic friction force is going to be mu k, the coefficient of kinetic friction, multiplying the normal force. So this means our kinetic friction force is mu k times mg. Now that's the only force acting horizontally on this car. So we can find the horizontal acceleration by using Newton's second law. I'm going to write it in the form A equals F over m. And the magnitude of the net force horizontally is just this mu k mg. Note that the force points to the left, and we'll put in a minus sign before we do the kinematics. And I divide by m, and this is the moment we find out it doesn't matter what the mass of the car is. I get the same acceleration regardless. And I'll go ahead and plug in my coefficient of kinetic friction. That was 1. And then g, we typically use 9.8. So we arrive at an acceleration of 9.8 meters per second squared. Notice that this is just a magnitude. I'm not attempting to include the direction in this number. We will need a minus sign before we start doing the kinematics, provided that we're using the standard coordinate system where rightward is positive. So for the kinematics setup, I now know that the acceleration of this car is leftward pointing and it's 9.8 meters per second squared. I'm going to call my initial position 0. That's the moment we hit the brakes. We're measuring starting from a new starting point. My final position, that's what I'm trying to get out of this problem, and it's already been given another name. It's called little d. And my initial velocity before the braking begins, that's the number we computed in part A. That's 33.2 meters per second. Finally, my final velocity, if I'm skidding to a stop, my final velocity is 0. So notice that once again, the time-independent constant acceleration kinematics formula is the one we want because we're not interested in how long this process takes. So we write the equation down, plug in the stuff that we know, and we should be able to solve for d. So my final speed again is 0. My initial speed, 33.2, and I need to square that. My acceleration, and the sign matters here, is negative 9.8. My final position is d. My initial position, 0 by assumption. We simply moved our origin there for the analysis of this part. So we go ahead and square 33.2. Subtract it from both sides, divide by the coefficient of d, and we can solve for d. Into 3 significant digits, I get 56.2 meters for the minimum stopping distance. And we're done. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.